TCP/IP is a suite of standard protocols designed for wide area networks. TCP/IP protocols map to a four-layer model: network interface, internet, transport, and application. At the base of the model is the network interface layer. This layer is responsible for putting frames on the wire and pulling frames off the wire. The next layer is the internet layer. This layer is responsible for addressing, packaging, and routing functions. There are three protocols at the internet layer. Internet Protocol, or IP, is primarily responsible for addressing and routing packets between hosts and networks. Address Resolution Protocol, or ARP, is used to obtain hardware addresses of hosts located on the same physical network. Internet Control Message Protocol, or ICMP, sends messages and reports errors regarding the delivery of a packet. The transport layer is responsible for providing communications between two hosts. There are two protocols at the transport layer. Transmission Control Protocol, or TCP, provides connection-oriented reliable communications for applications that typically transfer large amounts of data at one time or that require an acknowledgement for data received. User Datagram Protocol, or UDP, provides connectionless communications and does not guarantee that packets will be delivered. Applications that use UDP typically transfer small amounts of data at one time. Reliable delivery is the responsibility of the application. At the top of the model is the application layer. This layer is where applications gain access to the network. Microsoft TCP/IP supports Windows sockets and NetBIOS interfaces between user applications and the transport layer. Windows sockets provides a standard API under Microsoft Windows to many transport protocols with different addressing conventions. NetBIOS provides a standard interface to protocols such as TCP/IP and NetBEUI that support the NetBIOS naming convention for addressing. As we'll see, when an application sends data to another host, each layer adds its own information to a header that is encapsulated as data by the protocol in the layer below. When the packet is received at the destination host, the corresponding layer strips off the header and treats the remaining packet as data. The packet is then passed up the stack to the appropriate protocol. Now let's look at each of these layers and how they interact with each other in greater detail. The network interface layer is responsible for merging outgoing frames onto the wire and for pulling incoming frames off the wire. The mechanism that's used varies with each network medium. When the network interface receives a packet from the layer above, it adds a preamble and CRC. The preamble is a sequence of bytes that identifies the beginning of a frame. The CRC, or cyclic redundancy check, is a mathematical computation that is added to ensure that the frame is not corrupted. The frame is now merged onto the wire. When the frame is received at the destination host, the preamble is discarded and the CRC value is calculated. If the two values match, the destination hardware address is examined. If the hardware address in the frame is a broadcast address, or if it matches the network interface, the frame is passed to the appropriate protocol in the layer above. If the value doesn't match the original CRC value, or the hardware address is not of interest, the frame is discarded. Now let's look at the next layer in the stack. The internet layer is where packets are addressed and packaged for routing. IP provides a connectionless delivery service, meaning that a session is not required with another host before a packet can be delivered. The delivery service provided by IP is not guaranteed. Packets can arrive out of order or be lost during routing. Reliability is the responsibility of the higher layer protocols and applications. When a packet is passed down from the transport layer, IP adds its own header to the packet. The IP header includes the source IP address, where the packet originates, destination IP address, where the packet is going, the transport protocol initiating the request. The protocol informs IP at the destination host whether to pass the packet up to TCP or UDP. A checksum value, which is a simple mathematical computation used to verify that the packet arrived intact, and the time to live, or TTL, a value which determines how long a packet lives on the wire before it's discarded. This prevents it from endlessly looping around an inner network. If the destination IP address is identified as a local address, IP transmits the packet directly to that host. If the destination IP address is identified as a remote address, IP checks the local routing table for a route to the remote host. If a route is found, IP sends the packet using that route. If a route is not found, the packet is sent to the source host's default gateway, also called a router. IP on the router does 4 things. It decrements the TTL by at least 1 at each router, or more if a packet gets stuck at a router due to congestion. If the TTL reaches 0, the packet is discarded. Next, IP calculates a new checksum. Then it obtains the destination hardware address of the next router, and finally forwards the packet. This entire process is repeated at each router until the packet reaches its final destination. If a router receives a packet that is too large for the underlying network, IP will break the packet into manageable chunks. When the chunks arrive at their final destination, IP assembles the pieces into the original packet. This process is referred to as fragmentation and reassembly. Fragmentation often occurs in environments that have a mix of media, such as Ethernet and token ring. Let's look at how this works. An IP packet is received at the router. IP fragments the packet into 3 smaller packets. A new header is created for each new packet, which includes a flag to indicate that other fragments follow. A flag is not added to the last packet because no other fragments follow it. A fragment ID to identify all fragments that belong together, and a fragment offset to tell the receiving host how to reassemble the packet. All 3 packets are routed to the remote network. Even if they travel through multiple routers, packets are only reassembled when they reach the destination host. When the 3 packets are received by IP at the remote host, they are identified by the fragment ID as belonging together. Next, the fragment offset is used to reassemble them in the correct order. Finally, the reassembled packet is passed up the stack to either TCP or UDP. When IP routes packets, it needs to obtain the destination hardware address. IP relies on ARP to obtain hardware addresses of TCP IP hosts on broadcast-based networks such as Ethernet and token ring. When IP needs a hardware address, ARP first consults the ARP cache for the hardware address that corresponds to the destination IP address. If the mapping is not in cache, ARP builds an ARP request frame for the destination host's hardware address. To make future communications more efficient, the IP address and hardware address mapping of the source host is also included in the request frame. The frame is then merged onto the wire and broadcast on the local network. All hosts receive the request, and the frame is passed up to ARP. If the receiving host's IP address matches the requested IP address, an ARP reply is formulated with the requested hardware address and sent directly to the source host. When the hardware address is received, both the IP address and hardware address are stored as an entry in the local ARP cache. The IP packet can now be delivered using the destination hardware address. If problems are encountered during routing, the Internet Control Message Protocol, or ICMP, sends messages and reports errors to the source host. For example, ICMP will send a source quench message when traffic becomes congested at a router. Source quench tells a host to lower its transmission rate. A redirect message when a preferred route is detected. This could occur if a router becomes congested and there is an alternate route available. Or a destination unreachable message when there is no route available, such as when a line goes down. The ICMP message is packaged in an IP datagram and routed to the source host. The next layer in our model is the transport layer. The transport layer provides endpoints as a means to communicate between two hosts. In UDP and TCP, the endpoints are called ports. UDP typically is used to transfer small amounts of data. UDP has two main characteristics. It is connectionless, which means that a session is not established between two hosts before exchanging data. Instead, UDP messages can be broadcast so that many hosts receive the message. UDP does not guarantee delivery of messages. Packets may arrive out of order or be duplicated. Reliable delivery is the responsibility of the application. When an application wants to send data to another host, UDP builds a header that includes a source port, a destination port which provides an address for delivering messages, and a checksum value for the data and header. At the destination host, the packet is passed up to UDP and delivered to the destination port. TCP is typically used by applications to transfer large amounts of data. TCP has three main characteristics. First, TCP is connection-oriented, which means that TCP first establishes a session between two hosts before any data is exchanged. Second, TCP assures reliability by using sequence numbers and acknowledgements. Sequence numbers allow TCP segments to be split into multiple packets and then reassembled into the original segment. Acknowledgements verify that the data was received. And third, TCP uses byte stream communications, which means that the data is treated as a sequence of bytes with no message boundaries.